Hey folks, I want to work through my MyMathLab question with you. This one's kind of interesting because it has you put the Riemann sum in both an abstract notion and then also in a concrete notion, and then we compute these for large values of rectangles, ones that you wouldn't want to do by hand. So let's go ahead and work through that, and we'll see how this works. So in this case I'm reading, and we've got this function f of x, and let me get a pen there. We've got this function here, f of x, the sine of 4x, and we want to approximate the area underneath the curve between 0 and pi over 4, and we want to do that with a total of 40 rectangles. So before I go to enter the answer into my MyMathLab, let's go ahead and just work through this a little bit. If we're going to use the left Riemann sum, then writing this out abstractly, we get the sum from k equals 1 to 40 of f of x, and then we label that with the subscript k minus 1 delta xk. That is the left Riemann sum for a function with 40 rectangles. Okay. Well, we automatically get to make a couple of substitutions. One is that delta kx, or delta xk, is the same for all k. And in fact, we'll just call it delta x. And what is delta x equal to? Well, delta x is equal to the the right endpoint, which is pi over 4, minus the left endpoint, which is 0, all over the number of rectangles, which is 40. And if I do some cleaning up, we can rewrite that as pi over 160. Okay, great. So we can express this as pi over 160 for our delta x. And then the next thing is we can actually specify what this function is, because we were given explicitly this is the function sine of 4x. So we'll write from k equals 1 to 40 of the sine of 4 times x of k minus 1 times delta x, which we're writing as pi over 160. Okay, well, we can take this one step further, because although I'm not going to list out my partition, here is my partition here. My partition goes, we start at 0, and then it's 0 plus 1 pi over 160. And then the next entry would be 0 plus 2 pi over 160 plus, and we'd keep doing this, dot, 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 all the way up to till we got to 0 plus 40 pi over 160, and that gives us that right endpoint of pi over 4, whereas this was our left endpoint of 0. So here's a way of actually generating the values of the partition. So what we'd like to do is talk about, well, how are we getting those values? Well, it looks to me like we're going with this. We could think of this as what the counter is currently at, and then multiplying that by pi over 160. Okay. So what we're going to do is we'll take that summation, and in place of the partition number of xk minus 1, we're going to say that we want to grab the sine of 4 times, and then one way to think about this is that in this case we just have 0 plus whatever our counter is minus 1 times pi over 160. Okay, there's a lot of parentheses there, and I've still got to add my times this exterior pi over 160, which is my delta x. Yeah. So let's look at how we got that. Notice that when so first of all, I'm going to drop off that 0. Let's do that just to clean this up a little bit. But in another problem, if we weren't starting at our lower endpoint of 0, we'd have to put a 1 there or 2 there or whatever that lower endpoint is. So we've got 40, and then we've got the sine of 4 times k minus 1 pi over 160 times our pi over 160. So keep in mind, this is still the delta x, and here we still just have the sine of 4x k minus 1, but what we've done is we've selected a way of generating those values of the partition. And the way we do that is we start, first of all, we want when k is 1, we want this value to be 0, so we plug in a 0 there. We plug in a 1 for k, which would give us a 0 for this factor. And so we got 4 times 0 times pi over 160, or just 0. And then notice that when k is, say, 2, we'd have 2 minus 1, or 1 pi over 160, which gives us this second value here. So you can check that as you plug in different values for k, you get the different elements of the partition. Okay? So this is what we can go ahead and enter into MyMathLab. So let's go ahead and do that. Okay, folks, so we're going to go ahead and enter our answer into there that we wanted the sum from k equals 1 to 40 of the sine of, and then we wanted 4, let's see here, this is our numerator, so divided by, in the sine of, inside there we want to have a quotient, and we want 4 times k minus 1 times pi, all divided by 160. Now that's our functional value, and we want to multiply that inside the summand by the delta x, which is pi over 160. So the next thing it's going to ask us to do, and this is what I also wanted to show you, was to actually approximate this left-hand sum with summand from k equals 1 to 40. Well, that is certainly not something we want to do by hand. So I'm going to go ahead and open up a new tab here, and we're going to go to wolframalpha.com, and this is what I'm going to type in. So I want to tell it to do a sum, so I'm going to type capital S-U-M. That tells me to do the sum command. Then I'm going to open bracket, which starts the sum function. And then I'm going to go ahead and type in the function, the expression that I want to sum up. So in our case, we're going to do capital S-I-N, open bracket, 4 times parentheses k minus 1 times pi, which I'm going to just enter as capital P-I. And that was all in the numerator. I guess I better make this into a quotient. So there's the numerator of the expression inside the sine, divided by 160, and so then we can close our sine function. You see I just closed the sine function there. It's registering that it's closed, and then we're going to go ahead and multiply that times pi divided by 160. So that's times our delta x. Now I know that this looks a little bit maybe a little bit messy. Here's our sum command, and all I've done inside that sum command was give the function that I wanted to sum up. So the next part of the command is to type a comma, and then we're going to put an open curly brace, and we're going to tell it that we want to use k as our counter, because that's what letter I'm using here. I'm using the letter k. So we're going to use k as our counter. That tells it what our counter is. Then I give the starting value of the counter, which we wanted to start at 1, and the stopping value, which in our case we wanted to stop at 40. Then we close that brace for that information there. Then I go ahead, and the last thing I've got to do is close the functional argument for the sum command. Okay? There are probably other ways you could do this, folks. If you know another way, that's fine. This certainly isn't a test question because you have to use Wolfram Alpha. All right, let's go ahead and hit enter, and Wolfram Alpha will add up those 40 rectangles for us, and we get a decimal approximation of the sum. In this case, MyMathLab's asked us to round it to 3 decimal places, so I think I'm going to be entering in the value 0.500 as we round it. So let's go ahead and do that. 0.500. Okay. And we get a little pat on the back. All right, so now we've got our second question, and I'm going to return with that in the OneNote here momentarily. Okay, folks, so we're going to be working with the same question here. Oop, that's kind of small. I'm not going to worry about that. We've got the same function. The f of x, in this case, is the sine of 4x. And we're using the interval from 0 to pi over 4. And we're going to be doing this for n equals 40 rectangles. Okay, so let's go ahead and work through this. In this case, we're asked to do the right Riemann sum, which in a lot of ways is a little bit easier to express in the Riemann sum notation. So just again, let's start out abstractly. The general Riemann sum for a right Riemann sum is the summand from k equals 1 to the number of rectangles we're going to have, which in this case is 40, times f of xi, I guess I better use a k here, f of xk, to keep the counter the same, times my delta xk. But again, just like we saw before, in this case, all of our widths are going to be the same. So we'll write f of x k just times delta x from k equals 1 to 40. And what is delta x in this case? I'm just going to run through this one more time. Delta x is our right endpoint, which is pi over 4, minus our left endpoint divided by the number of rectangles, and that simplifies down to being pi over 160. Okay, so there's our delta x. So we could go ahead and plug that in now if we wish. Okay? And in fact, I'll take that one step further. We know that our function is the sine of 4 times whatever value we're going to be plugging into it, times pi over 160. So this is the area of one of those rectangles. I'm going to repeat that procedure 40 times, add them all up to approximate the area underneath the curve. Okay, great. So the next thing I want to do is somehow replace this abstract. This is the kth element in our partition. Okay? And remember, our partition is going to go like this. It's going to go 0, comma, 1 pi over 160, comma, 2 pi over 160, comma, 3 pi over 160 until dot 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 until when? Until we get to 40 pi over 160. Those are the 41 elements in the partition. This one plus this additional 40. Those are the 41 elements in the partition. And in this case, I only want to be grabbing the last 40 of them when I do this procedure. So the first number I want to pick is 1 pi over 160. The next number I want to pick is 2 pi over 160. So how are we going to tell our summation formula to do that? So what we're going to do is say, okay, we'll still start at 1, end at 40. This is the sine of, and then here's the crux of it. What are we going to put in this position right here? To tell us to make sure that we are grabbing, to make sure that we are grabbing the correct value, we're going to go ahead and enter in k, whatever our counter is, times pi over 160. So we've got that expression gives us, notice when our counter is 1, that's going to give us that entry right there. And when our counter is 2, that's going to give us that entry in the partition right there. So this is going to sum these up correctly, and then we simply multiply this by our pi over 160. Okay. So I'm going to go ahead and enter this into my MyMathLab. So folks, into my MyMathLab, I'm going to tell it to do the summing from k equals 1 to 40 of, first we tell it the function height. So we've got the sine of, and I want to have a quotient there, so we'll do 4 times k times pi divided by 160. So that's giving us the correct functional values for each of the as the counter k runs from the values from 1 to 40, times then the width of each interval, which also has this expression pi over 160 in it. Okay, so now we're asked to go ahead and approximate that right Riemann sum. So I'm going to do this in my MyMathLab again, or Wolfram Alpha again. I'm going to run through it a little bit faster this time, but again, I want you to see how this formula works. So we're going to do the sum, left bracket. So this is how I type my sum command. And let me just put this in here. What you do is you put your formula, comma, then you do your counter variable, comma, then your first value in the counting, and then your last value in the counting. And that's what you enter in. Notice that I've got the sum formula opened with a bracket, closed with a bracket, and then I've listed my formula here, and then I've got open brace. I tell it what the counter variable name is, I tell it the first value and the last value. So let's go ahead and actually enter that in. So I'm going to put in our formula here, which was the sine of, and in my math, or in Wolfram Alpha, I have to do sine with a bracket, not a parentheses. 4 times, and then we had the quantity k times pi divided by 160. Close the sine bracket, multiply all of that by our width, which is also pi over 160. Folks, I use the lowercase letter pi for pi. That's probably fine, but I believe technically my Wolfram Alpha asks for a capital pi. It'll take either, but it asks for a capital pi. Okay, then what's our counter variable name? Well, in this case, we're using the counter k. What's our first value in our summand? We want to sum from k equals 1 to k equals 40. and we hit enter, and my Wolfram Alpha will crunch that for us. Notice in this case we also got the value 5.00 if we're rounding to 3 decimal places. Folks, that won't be the case when you do this, or this likely won't be the case when you do this. This just happens to be, I think, a coincidence of the numbers the algorithm gave me. Okay. So then the last thing we're asked to do is the midpoint method. I'm going to do this one a little bit faster here. I'm just going to go ahead and put it in, and then I'll let you see what your questions are on it. So we're going to enter in the sign of, same thing as before, 4 times, that's just the function. Now we need a way of getting the midpoint each time. Okay. So how do we construct the midpoint? We construct the midpoint by adding the 2 endpoints together in the kth interval and then dividing that by 2. So this is going to look a little bit messy. I'm going to go ahead and enter in my pi divided by 160. That's the part that we see up here. So that all I'm going to be entering right now is how do I tell it to grab the midpoint of the interval. So how do you tell it to grab the midpoint of an interval? You're going to add up the k value plus the k minus 1 value. And then you're going to divide that entire result there by 2. So that's how you tell it to enter in the midpoint. Okay? And then we'll multiply that. Notice I'm outside the sign now. We're still going to multiply this by pi divided by 160. Okay? So I'll go ahead and close and hit enter. We'll check it. Yep, that worked. Now the only thing I want to say, folks, is right here, and hopefully you can see where my mouse cursor is. Right here, I could have actually put the values 2k minus 1. And that's what you might see MyMathLab do if you ask them to help you solve this problem. Because you could combine the k plus k to give you 2k right there, and then we'd have minus 1. Okay. I'm not going to do the summing for this one. This video's gotten long enough, but you would just follow, you would enter in this exact same formula into our Wolfram Alpha. Please, folks, let me know if you have any questions over this. I hope this video was helpful.